Some of the most common types of two-dimensional motion problems are projectile examples, and this particular example is very indicative of questions that would be asked. So the setup is, suppose a ball is kicked from a 2-meter high ledge at 20 meters per second on an angle of 37 degrees. And then typical questions would be, how high does it go, how long is it in the air, and how far does it land from the base of the ledge? So I've drawn the diagram here to give you a sense of what's happening, and if we go back and just cover up the questions for now and analyze the motion, right? From this cliff out across the space, this ball is going to be launched into the air, peak at some point, and then land some distance off horizontally away, right? What we need to keep track of, as we discussed in the previous videos, is that in this section, the initial velocity is comprised of two vectors. One is horizontal that we call Vx, and one is vertical that we call Vy naught. Now Vy naught is only the vertical velocity at the initial conditions and changes as the ball propagates through the air. Vx, on the other hand, is a constant velocity that continues the entire time. And so then there are questions about certain positions, like here would be how high it goes. Dy is a question. It's important to note that at this particular location, we know that Vy is equal to 0. The time frame for how long it takes to move across from one point to the other would be the entire process from here to here. And so we have some final velocity down here that would be angled off like this, that we actually don't know, because that velocity is not the same as 20 because it's not at the same vertical height, right? Keep in mind, projectile problems are only symmetrical if they happen at the same height. So this final velocity is unknown. What we do know, however, is that Vx will have a horizontal component down here that is the same as the original Vx up here at the top. We still do not know Vy final, but we'll be able to figure that out if we need it for the trip across the field. Some other indicators that are important here is in terms of vertical. If we're talking about this position here at the end, if I were to take the ledge and stretch the ledge's edge out across the page, we know that the displacement of the final position, or dy at this location, would be -2 meters. We know all of this based on an acceleration that would slow the ball down and speed it back up as on the way down, based on an ay equal to g, and in this frame of reference as -9.8 meters per second square. And so to back up just a click, we notice that we've set up this problem where we're calling this positive x and we're calling this positive y. And so in analyzing the question, right, this is a typical schematic or diagram of the situation that matters for answering our 3 questions. Now, before we can move on to answering our 3 questions, what we need to do first is resolve V naught into Vx and Vy naught so that they can be applied through our x and y table solving the problem. In order to do this, I find it most useful often to redraw this portion of the diagram on a separate piece of paper or in a separate location of the picture. And so I'm going to do that down here and save my diagram for just another moment. So if I redraw my initial picture and I say V naught is equal to 20 meters per second on an angle of 37 degrees, and then I relocate my horizontal and vertical components, I see that I have a horizontal component Vx that looks like this, that when drawn head to tail creates a Vy naught that's here. These two are perpendicular, and this is a right triangle with an angle of 37 degrees, and so I can calculate Vx as being 20 times the cosine of 37, which I believe comes out to be 16 meters per second, and Vy naught equal to 20 times the sine of 37, which I believe comes out to 12 meters per second. And so now I can take that knowledge and fill it in on my original diagram. And so if I went back to my original picture and I squared this up where I had it just a moment ago, I could fill in the fact that I now know that Vy naught is 12 meters per second and Vx is 16 meters per second. Now, a key thing that I mentioned in a previous video is once I've taken the original velocity, V naught, which was on an angle, right? The angled vector does not match the frame of reference. And since I've taken that and resolved it into two components, one that is an x component and one that is a y component, these are the numbers I'm going to use to operate through the remainder of my problems. Notice that as I drew my vectors, they were either perfectly perpendicular horizontal, where I'm measuring dx along this direction. I'm measuring dy along this direction. I'm measuring velocity x in the horizontal direction. I'm measuring velocity y in the vertical direction, right? The acceleration in the vertical direction we know is down at negative 9.8, which is also vertical, and we know that the acceleration in the horizontal direction is 0. Taking all of that information, we can generate a table of variables that matches up to our scenario here, where I end up with a list that is comprised of both of my directions, x and y. And so what we have so far is that Vx is equal to 16 meters per second, dx is one of the questions, t is unknown. That's all for the horizontal components. In the vertical direction, we now know that Vy naught is equal to 12 meters per second. Again, both of these are positive based on the analysis that this was to the right and up, right? And so these are both positive values, and I've inserted those positive signs after I did this calculation based on my frame of reference that I identified at the beginning. All right, so then I do not know what Vy is, but I do know what it is at certain locales, which I'll use to my advantage in just a moment, right? And then, of course, dy I do not know either, but that will depend on which locale I'm at as well. And acceleration, of course, is negative 9.8 meters per second squared. And then, of course, time is also unknown. Generally, I've asked these three questions: how high does it go, how long is it in the air, and how far does it land, because that sequence seems to be the most logical for answering. But of course, these could be out of order, so do recognize that you may have to solve for something out of order in order to utilize those variables in different locations in this table. However, if we begin with how high does it go, then we know that based on this picture, at the highest point, dy is the question. That would be how high it goes, right? However, that dy, if I solve from V naught to Vy, right, keeping in mind V naught starts here, Vy naught goes to Vy at the top, sorry. Vy naught starts at the original height of the ledge, Vy goes to 0 at the highest point. So this dy plus 2 will be the total height at that point. And so first we need to find that dy, where at that dy I know that Vy is equal to 0. So I'm going to come back down here to my table and say at the top, right, I know that Vy equals 0, and dy will be the question, but the height will be equal to dy plus 2 meters, so that I can indicate that additional 2 meters of the ledge. Based on that information and the rest of my table here, right, I can solve that pretty easily with my v squared equal to v naught squared plus 2ad formula. Here I'm using dy and vy's to indicate vertical motion, and then I can also go ahead and change a to g if that's easier for understanding, although I've written it here as a. Either one is acceptable because we know the acceleration in the vertical direction is g, right? And so taking that information and the table that I've generated in combination with what I am at the highest point, I know that Vy is 0, I know that Vy naught is 12, I know that g is 9.8, and 2 times negative 9.8 is negative 19.6, and then of course dy is my variable that I'm in search of, right? And so I square 12 and get 144, I subtract 144 to this side equal to negative 19.6 dy. Then I go ahead and divide by 19.6 and I get a dy equal to 7.3 meters. And then of course I haven't answered the question because the question was what is the height? And so I have to take dy and add 2 meters, and so my height is actually 9.3 meters. Moving from that on to the second question for how long it's in the air. If I take a look again at this original diagram that I had, in the original diagram, here is the final position. I know that from my starting position to my final position, dy is actually a negative 2 displacement. So if I reorganize my chart for at the end, as opposed to at the top as we did in just the previous picture, I know that at the end, dy will be equal to 0. No, I'm sorry. I know that at the end, dy will be equal to minus 2 meters. I do not know what Vy will be, although I could calculate it if I was interested in knowing. And the rest of my table still applies. So I still know that Vy naught is equal to 12, and I know A is equal to negative 9.8 meters per second squared. So in order to find the time, I can simply ignore the Vy and use an equation that contains Vy naught, A, T, and D. That equation, of course, is dy equals Vy naught T plus 1/2 AT squared. Plugging in the numbers, I end up with negative 2 equal to 12t minus 4.9 t squared. And as we've seen already, this is a quadratic that will need to be solved. Your skills in your calculator should be fast enough now that you can solve that pretty easily. When you solve for t, you'll get two values, 2.6 and negative 0.2. And if I go back and look at my diagram, it should make sense that if I were to trace this parabola backwards to where this would have started had it started at negative 2 meters, from here to there is a very short time frame that corresponds to the negative value of time, right? This is a negative value of time that's unrealistic, which is where this negative 0.2 is coming from. The full 2 seconds is the time it takes for it to go all the way up, peak, and then all the way back down to a d equal to negative 2. And so based on the fact that by the parabola analysis, but also by the fact that time can't be negative, we know that t would be equal to 2.6 seconds, right? So don't do anything tricky. You don't have to do anything tricky about trying to solve from the top to the end based on what we did for part A. All we need to know is the displacement, and the displacement is negative 2 at the end. And so that's a pretty easy calculation in terms of time. Once we have that, we also know that at the end, the velocity in the horizontal direction, Vx, has remained 16 the whole time, right? And so Vx is traveling at a constant velocity. Vx is equal to constant, right, of 16 meters per second. And so the third question about how far it lands from the base of the cliff is simply a question of dx. Dx, going back to my original table that I wrote down here on the bottom, dx is a function of Vx and t. Those two things are the only things, because in the x direction, the velocity is constant. And since the velocity is constant, we know that Vx equals dx over t. and all we have to do is fill in what t is. Now, it's important to note that we can solve for time at different locales, right? But we haven't done that. We didn't do that anywhere else on the page so far. So this 2.6 seconds was the total time it took to get to the bottom. And so this t is the appropriate t that we will use here. And so this equation becomes 16 equal to dx over 2.6. We simply multiply by 2.6 and we see that dx is 41.6 meters. The only additional question that may come up a little bit later on as we go is for solving for v. And so you can imagine that your last step will be to calculate the final velocity of this vector as it crashes into the ground. I will leave it to you to determine v in this example.